a knack for teaching ground school, so hopefully you'll enjoy this as much as I do. For those of you that have already been kind of following along with me, if you thought that the general subjects and performance and all that other stuff were fun, right? I told you all those were kind of my favorites. Aviation weather is undoubtedly my favorite, and I'll probably say that every chapter that we have. But it's a fantastic program. I only get 2 short hours to go over the aviation weather meteorology for pilots. It coincides with chapter 6 in your guided flight discovery. Anybody have that book? Anybody not have the guided flight discovery? No? So everyone does have the book, right? It looks a little bit like this. This is the private pilot exams, but it has the little airplane on the front. It says private pilot guided flight discovery. This coincides hand in hand with chapter 6, okay? So as we go through, if you have any questions or whatever else, jot them down. We'll continue through the class. I'll certainly address as many of your questions as you want and as long as we can. But remember, once you get home, the important thing is, the expectation is you've already read the chapter. So, that's where everyone should be already. Chapter 6, A to Z, just all the way done. We'll go through this. We'll have a nice little lecture. I'll ask you guys some questions, guided discussion more or less, so that you guys can provide some feedback. Some of that's required. But at the end of the day, it's important. Go back and look at chapter 6. Reinforce the material. There are sample questions in chapter 6, section A through D, right? Go through all of those sample questions and answer them. When it comes time to take, a little private pilot exam, easy breezy, just run through, hey, look, I already know these answers. These should come relatively simple for me, okay? This is very, very basic Aviator 101 stuff. Now, is it new to a lot of us? Certainly so. Not new to me, not new to your instructors, okay? Yeah, we know this stuff. We're familiar with it, but it's new to you guys, a lot of you. So that's why go back and reinforce the material. Super, super important. Okay, and especially weather, because does anybody not like the subject weather? Oh, of course, right? Anybody else not like the subject weather? No, everybody enjoys it, really? That's surprising. Because what I find out more often than not,
there's only one honest
There's only one honest guy in here. So what I find more often than not is that the pilots really don't have either a good understanding of it, or it wasn't brought to them properly, or they respect the weather, but it's always nice and clear out here, so there's really not much need to get a weather report. Whatever the excuse is, once we start drilling down and asking Coriolis Effect and all these other things, oh man, you get the glass over the eyes look. All right. So without further ado, here we go. Here is your atmosphere. All right, this is how it's defined. And anybody watch the new, and if you haven't, try to watch it. It's an Amazon Prime movie, and it's called The Aeronauts. Has anyone seen that?
No.
Try watching that. That's pretty cool. And I'll tell you why it's pretty cool. Because this was a long, long time ago when pilots were balloon pilots. That's what they were. Nobody had flown a heavier than air machine yet. So this scientist and a pilot, who happens to be a female pilot, ride up into the air, into the atmosphere, and they gauge and they take measurements, and they kind of find out what's going on in the different layers of the atmosphere. It's kind of a neat story, and it's a good movie too. Well, anyways, that's what we have going on here. Now, surrounding the Earth, you've got all this atmosphere, all this weather around us. The part that contains mostly everything that we're interested in is the troposphere. And that's very, very low to the surface. Low to the surface meaning somewhere mid-30,000s. That's how high it is. It doesn't exist any higher than that. And it expands and contracts depending on air density. I told you guys already, air density positively rules everything for aviators. Well, it certainly does. And it expands and contracts that tropopause, okay? The tropopause is nothing more than the thin layer between the troposphere and the stratosphere. We can see here in this guide, and this just comes out of the Advisory Circular 00-6 Bravo, which was updated in 2016. It just shows us with different temperatures and a couple other things as we go up. Some pilots are going to fly in the stratosphere. That's fine, fantastic. Once you get something turbine powered and a lot faster than 4.1 Mike Echo, you probably go up into the stratosphere, okay? Until then, everything we do is in the troposphere. So there's some other parts around our atmosphere, but we're really not interested. Let's stay scoped and focused on that part that we're interested in right now. Okay, so part of this discussion with weather, and part of it that really amuses me while I'm teaching this year after year and decade after decade, geez, is that we have to think about a theory. This is essentially your weather theory. You hear, all right, weather theory, I have to know something about that. And then I also have to know about weather services. How does this government provide information to me useful as a pilot about the current and forecasted weather conditions, okay, in the recent past? But without talking weather services, back to the weather theory, we have to discuss what happens if such things happen, like maybe the Earth stands still for just a moment. It will never stand still. Okay, if it did, we would be tumbling all over the place. But in my head, I need to think for a second, what if I could make the Earth stand still? And I have to think about that concept. Now, while you're doing this mental exercise with me, keep that type of mental flexibility alive, okay? Allow yourself to have some aspects of this weather theory that you know are impossible. But we're going to take a look at it so that we can build upon and consider other aspects together collectively, which lead us to a more complete picture of what weather is happening around us, okay? So we take all these theories and we'll put them all together, and that's a nice little close picture and approximation to what's happening. Okay, the first thing first, and you guys have heard this, I'm sure, before or read it, and that is, what is the driving force behind all of the weather that we experience? Now, if you have a flight instructor certificate, you're not allowed to answer any of my questions. Okay? So, what is the driving force behind all of our weather? Heat. Okay? Does that make sense? That's the easy answer. Pilots will do that. Experienced aviators, they know that. Okay? But does it make sense to you guys? Think about this for a moment. What's the only thing that will affect our little atmosphere? It's the transfer of the sun's energy. That's it. That's the only thing that will make any difference to us. So if I transfer the sun's energy to Earth and it's released and there's some sort of heat exchange, fantastic. This causes some sort of a circulation. Anybody have an aquarium before? Maybe, hopefully. This group has been so hard. Okay? No one has had an aquarium with a fish in it. Okay. Has anyone seen a picture of an aquarium or been to a place where they had an aquarium, such as Banyan Air Services in the terminal, right over there? Or do we need to everybody jump in the van and go right over there and look? Yeah, of course. Yeah, we need to do something, get out of here. Plenty of coffee for everybody? Okay, looking kind of dazed over. The aquarium. What happens inside of an aquarium? That's my question. Anybody got any great ideas?
They change the water, they rotate the...
The water flows, okay? Just so you guys know, if nobody gives me any kind of answer at all, I think you just don't know anything, okay? Don't let me think that you don't know everything, because then I'm just going to keep on rambling on. All right, so the water inside of an aquarium has a flow to it, has a circulation. That's the exact same. We are essentially in a large aquarium. And this water that we breathe, well, it's just thin water, it's air. But it has physical characteristics and behaves very, very similar to fluids. In fact, aeronautical engineers will study air as a fluid, the same as they study water as a fluid, or any other fluid as a fluid, okay? So circulation exists, and we need to think about us living inside this aquarium. Fantastic. Well, how does the circulation exist inside of an aquarium? Any ideas? Anyone at all? I would love if you have an idea.
It's an electric pump.
Not you. Anybody got some ideas?
Moon? No.
I'm sorry?
Moon studies.
Moon?
Yes.
An aquarium for fish that you'd have inside like a house.
Electrical pump.
Okay. What does that pump do?
Puts more water and sucks out water on the other side.
Okay, it causes some sort of flow,
Yes.
right? Think about this for a second. I got an electric. Does everyone know what a pump is? Because I'm starting to believe that a lot of people are maybe just not knowing what a pump is, right? An electric pump. Because when we get to fuel systems and all that, which thank goodness we've already done, it gets really fun if you don't know what a pump is. It's a little thing, it's submerged inside a fluid, inside the water. And then it moves fluid, or in our case that we're talking about now, an example, that aquarium, it moves that water in one direction. Okay? All four sides of this aquarium contain all of the water. So as it moves water in one direction, is any of that water escaping the tank? It's important to know that. Easy for us to remember that. That question is stupid. Yeah, it's stupid, sure, until you start looking at circulation. Okay? Because the water, our water, flows back to the pump, back to the heat being released and the air rising. Okay? So just like water doesn't just flow outside of this aquarium, the air doesn't flow outside of our troposphere either. It's all contained within that. All right? Very important element. Normally it doesn't take me this long to get through it, but hey, you know, we're having a great time. Okay, so think about this for a second. I have the sun, and the sun releases a tremendous amount of energy. I'm with the, does anyone not agree, right? But does anyone not agree with that statement, that the sun releases a lot of energy? Okay, so everyone agrees on that.
Yes.
The sun releases this energy. It passes through all of those layers of the atmosphere and then heats the Earth's surface. Now guys, I got a real building block style of teaching. Okay, it's been effective for a long time. In order to get to Z, we got to first do ABC, right? We got to just build these blocks all up.
Yes.
So I need to make sure that you know, if it sounds like I'm telling you something very simple, there's a 100% perfect reason why I'm telling you something very simple. Because 4 more steps and it's not going to be simple anymore, but we needed to have all agreed upon those other steps, okay? It's very important. All right, so I got the Earth's energy, or correction, the sun's energy. It travels through space, fine, makes contact with the Earth. The Earth absorbs some of that energy. It absorbs energy, okay, in different levels. Let's take a little closer look, and not an Earth look view, but maybe even just a parking lot look view. If I walked outside on a hot summer day and I wasn't wearing shoes, because I was born in Florida, right? Whatever. I wasn't wearing shoes, and I walk on the grass. Okay, fine, kind of comfortable, nice and easy. I step off that grass, and I step onto the hot black asphalt pavement. Is there any difference in the way that feels? There's a lot of difference. So the amount of heat that's absorbed is different based on just a real close microscope look at the Earth, based on what I have here. Now that difference applies also to the difference of water or land. All right, so keep that one parked in your mind for a moment. But what happens here, the sun's energy is absorbed by the Earth, and then the Earth releases some energy. Very important next step. So now just another small step forward from that. I need to understand how air behaves based on temperature. Which one weighs more? Hot air or cold air? Or do they both weigh the same?
Hot air tends to rise.
That's correct. Why does it tend to rise? Okay, we got some keywords out there. Less dense. This is where we go from the memorization to the understanding and application levels of learning. Okay? So which one of these air packets, if I had 2 packets of air and one was hot and one was cold, which one would weigh more?
Cold.
The cold air. Okay? Any ideas why?
More dense.
Oh, that's okay, great. What do you mean more dense? Can we quantify that? Can we figure that out? What does more dense mean?
Has flowing around.
Okay, so we got molecules. Everybody's okay with this too? Okay, so you have some molecules and whatever percentage we have different elements. All right? Cold air, the molecules don't move as fast. So that cold air will tend to have more molecules within the same volume. Warm air, those molecules move very fast and they expand, they're away from each other. It weighs less per volume. Earlier when I was talking about the aeronauts, these guys that were flying the hot air balloons, how did they get up there in the first place? The heated air. Or they could use lighter than air, some sort of a gas. I'm not a balloon guy, so I don't know what kind of crap they put in those things. But it makes the air density less. In other words, there are fewer molecules, right, per volume. Well, that's what's happening here. Keep in mind also that the sun heated the earth. The earth then released, or the earth's surface absorbed the sun's energy. The earth then releases the energy into the atmosphere. And that transfer that occurs there heats this surrounding air. As it's heated from below, now the air begins to rise. So this is why we have circulation. This is why heat drives the entire thing. Right? Heat drives all of our weather that we're familiar with, that we experience. So heat rises. This is a very, very simple, in fact, there are 3 known cells. This is a very, very simple circulation pattern on an Earth that does not move. As that air rises, it pushes against the tropopause, where we have a different layer of air, and then it moves towards the poles, far away from all the heat that occurred right here. As it goes towards the poles, it cools. As it cools, what happens to the weight or the air density? It increases. So then that descends and comes down. Well, why does it come back here? The exact same reason that water went back into the pump on my aquarium. Right?
Yes.
Through advection, it goes right back to where it started from. And everything continues to go. All right. Any questions yet so far? This is the main idea. Pilots will remember the main idea that fast. Next thing you know, we start talking Coriolis Effect, and I don't know what happens. A bunch of crossed eyes and then good night. Okay? Any questions at all on this? Whew! Fantastic. All right. Here's another example, small scale circulation. So I've got cool, dense air that's moving down. Warm, light air that's moving up. Advection is what brings that together. So the fact that we have advection brings the cool, dense air from wherever it went, whatever model cell I have that takes this over and causes it to cool down, back into the warm, light air. All right. We talked earlier, we said we're going to have some ideas, some theories. One of those ideas is the Earth did not move just now. So it would be very, very simple for me to stand anywhere on this map and for me to say, okay, 100% I know where the surface winds are moving. Would you guys agree with me that over there is somewhere near Western Africa? Is this Western Africa, somewhere around here?
Yes.
Okay. So if I were standing somewhere in the vicinity of this part of that continent, right here, where is the circulation? Where do I see wind moving if I'm standing right there where I was just pointing?
From north to south.
From north to south, okay? Easy, right? Super, super easy. Well, what's Coriolis effect? Anybody got some fantastic answers for Coriolis effect? Anybody remember what it's called? You memorized it? A lot of pilots have no idea what Coriolis effect is, do we? Let me explain what Coriolis effect is, first teaching only to the rote level of learning. So only if you want to memorize the answer, which is not really where we want to be, but at least get myself started. The Coriolis effect in the northern hemisphere will move the direction of the wind 90 degrees to the right. Anyone ever heard of that before? Maybe, something. A lot of us don't know what it means. A lot of us don't know why it's important. There's so many different ways that I can apply this. There's so many different ways that I can use this to help myself gather better situational awareness about the weather. Well, why? Why does Coriolis Force exist? What in the world is going on with this thing? Let me explain why. And then we'll talk here on the screen, and I'll give you some examples as best that I can. Okay, Coriolis effect is our perception for which way the wind is moving. All right, team, listen, I'll tell you, the wind doesn't change the circulation. The circulation is exactly the way that it should be. If viewed from outer space, if viewed from a third party point of view, right? I'm just at a fixed point in outer space. That circulation exists precisely the way that we saw it in the other diagram. But we're not in outer space. We're on the record player. Okay, I'll get to a record player. Hopefully everybody's familiar with that. That class was fun years and years ago. We are on the record player. We are on the machine that's turning around and around and around. You don't feel the movement. We don't perceive the movement. And as humans and certainly as pilots, guess what? The world revolves completely around us and nobody else. So we have no problem at all knowing that there is no movement as far as I'm concerned. But we trust that it exists, right? There's certain things that we don't have to see, and we trust these things exist. Fine. So here we have a record player. Please tell me that everybody knows what a record player is.
Yes.
Okay. Anybody not know? Turns around and around. Okay, fantastic. So if we take a record player and that record player is turned off, like it was in my previous example on the Earth. If I take that record player and I put a marker in the center of the record player and I move the marker, what does that line look like?
Straight line.
It's a straight line. All right. Didn't even have to read chapter 6 to get that one. Perfect. All right. Now, if I turn the record player on and I take the marker and I put it in the center, what's the record doing? It's moving, okay? But I take my marker and I just move it in the same exact straight line that I just did. Do I get a straight line on the record player?
No, you get the curve.
It's a curved line. That is your Coriolis effect. Okay? It's the exact same thing. Now, we are not the marker for the Coriolis effect. Remember, we are on the record. We are on the item that's moving. So the wind is the marker, essentially. That wind will still move in a straight line. But what's our perception? Our perception is that this thing was 90 degrees to the right. And that is precisely how scientists were able to define and predict and forecast the winds aloft. All right, taking a look at the isobars, which is nothing more than a line of equal pressure, they could identify where the winds aloft were because it was exactly 90 degrees from the true flow, and that true flow was exactly parallel to the isobars. Okay? So this is your winds aloft. The wind does move in a certain way, but because of our perceptions, it's 90 degrees deflected to the right. All right, I had before in the past a couple of classes that were really kind of foggy about record players or whatever the case may be. So again, illustration of Coriolis Effect. I got number one, this thing's moving somehow or another. We got a straight edge presented there to this record player, this turning disc. And then we were able to take a pencil and move it, and you could see as the pencil moves what type of a line is formed. Okay, why is that important to weather? Boom, here it is. Pressure gradient force, or the force that makes the winds move, will flow from areas of high pressure to low pressure. These areas are defined on surface analysis charts and constant pressure charts, prognostic charts. These things are defined by lines of equal pressure. So if I see this line of equal pressure, that's called an isobar. I see this line of equal pressure. I know wherever that center of the high pressure system is, air is moving towards the low. That's your pressure gradient. Now, something else interesting about a pressure gradient, and I got to start using some terms again that we'll see how this goes. Anybody seen a contour map? Are you familiar with a contour map? I would hope so, because what kind of map do we have as a sectional? The Miami sectional map, the Miami sectional chart, right? What kind of map is that? Anybody? It's hard to see because Florida is very, very, very flat. But if you were to get the sectional chart for Albuquerque, what would that sectional chart look like? Any ideas?
Colorful.
Colorful. A lot of different colors, right? The colors correspond to elevation above mean sea level. I've said to everybody that this area is great for flight training. You know why? Because the weather is great, the people here are kind of okay, right? The airport is nice to go to, but Florida is a terrible place to learn how to fly airplanes because there's really no challenge to it at all. It makes it easy. It makes it really, really easy. But you have no terrain features at all to deal with. So a lot of this stuff you'll never see. And if you don't see it, pilots don't even think it exists. Okay? It's a contour map. That's exactly what that is. A contour map showing and describing lines of equal elevation. And then they're color-coded to show me at a glance where I may find very large changes in elevation. Okay? If I have one of these areas, very large changes in elevation, the lines, the contour lines, are very close together. So contour lines that are very close together indicate a very steep terrain feature, a very steep hill or a cliff, right? The same holds true for isobars. If the isobars are very, very close together, think about that as a very steep terrain feature, something with a very steep slope, okay? So the pressure gradient force is much larger. The winds are much faster. Okay, got a couple other things here. Great. What is this? Coriolis Force. We were just now talking about that for a little bit. All right. Coriolis Force acts in the opposite direction. Well, we say acts. Whew. If you guys want to get together one time and talk to me about Coriolis force and centrifugal force, all right, it'll be a great discussion. But maybe outside the scope of this, and really who cares, because everybody has their ideas. But Coriolis force, again, what is that? That's our perception, okay? That's our perception of something existing. It's very similar to us flying an airplane and saying that centrifugal force moves a notepad across the dashboard. Forget flying for a second, just go out in a vehicle. So now I'm stuck to two-dimensional driving, no hills or anything else, flat land. If I'm driving a vehicle and I have something, my cell phone sitting on the dash, and then I turn my vehicle one direction or another, what happens to this cell phone? It moves towards the outside, right? But it didn't really move towards the outside. I moved the vehicle that direction. And the cell phone resisted movement and stayed on that direction, right? Makes sense? Same type of thing going here with Coriolis force. So it exists, I perceive it, we'll say, right, we got there. This is the resultant wind. It's 90 degrees. 90 degrees in the direction of the actual flow of the wind. That's my perceived wind. And the wind that will affect our airplanes while we're flying. Okay? Have I lost anybody so far? This stuff usually gets breezed by so fast. Boom, 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 boom. Just remember that you got heat drives the weather and 90 degrees to the direction of the wind. Okay, that's all you got to remember, memorize. But have I lost anyone so far? Because this stuff is important. No, everybody's fully engaged, right? Man, I hope so. All right. I get a lot of north and south. I get that every time. Okay, that's your resultant wind. Where's the resultant wind? Parallel to the isobars. So at a glance, weather forecasters can predict exactly where these winds are going to go and the speed of the winds, essentially the wind velocity, the direction of, and the magnitude. Pretty neat. You can do the exact same thing while you're doing your cross-country planning. We don't go too far during our cross-countries. Go from here to Naples. The furthest we go is Jacksonville on your commercial program. Okay, whatever. But I can start to see that I'm not going to fly a 172 for all the rest of my life. I might fly something a little bigger and faster. Okay, if I'm flying something bigger and faster, now this becomes important. Okay, again, my pilot's going to sit there and close their eyes because in the 172, we don't even cross one line, right? You're not always going to fly a 172. So we said high and low pressure systems. Where is the wind moving from this high pressure system? Which way is it moving? Well, it's going towards the low. Same thing here. It's going towards the low. Right? In varying degrees, I have wind that's moving from this high pressure to that low pressure. But we have Coriolis. And Coriolis won't allow this to go in a straight line. Which way are the winds moving instead? 90 degrees in the direction of rotation. So it goes from high to low. If I just turn that 90 degrees, I've got circulation patterns that go around the high just like this. In the northern hemisphere, which, forget about it. Southern hemisphere just goes the other way. Who cares? All right? But everything kind of scoped down to the northern hemisphere. That's the direction of my rotation. On the low pressure system, it goes in the opposite direction. Okay? Thank you, Coriolis. Well, that's just how things go. Helps me plan and predict flights. Okay. All of this works well and good as long as there is no friction. So if I'm above approximately, this is not a guaranteed, this is where it cuts off, but somewhere approximately 2,500 feet above ground level, the effects of friction are negligible. So once I go to 2,500 feet, that and above, it's almost negligible. This will hold true, where you have the resultant wind exactly parallel to the isobars. Once I get below, and I'm looking at winds below 2,500 feet, I have a little bit of friction. Friction from buildings, vehicles, people, grass, trees. You name it, it's there probably, right? Whatever exists is there. Terrain features, all sorts of stuff has some friction. Okay? That decreases the effectiveness of Coriolis. Anybody look at a winds aloft chart? No, of course not. Why would we look at that? You just follow the magenta line on the GPS receiver. We in 2020 or am I back in grade school here? What are we doing? No. If we look at a winds aloft chart, you'll see that stops at 3,000 feet. And then it also doesn't mention any information at all for an area where the surface is then 1,500 feet. So if I go out to Denver, they don't have a 3,000 foot winds aloft forecast. Well, because it would be in the middle of a rock somewhere. There's no wind there. They have a 6,000 foot winds aloft forecast because it's 6,000 feet pretty close. We're within 1,500 feet of the surface. Those winds change. It changes and moves across the isobars toward the low pressure system. Now, those of you that memorize the test, and I know there's people that memorize tests, that should sound like a very familiar question. What happens to Coriolis effects and friction of force? It moves across the isobars towards the low pressure system. I know, you guys remember everything. Don't know how to use it, but remember it, okay? Okay, fantastic. That's what's happening. How else can I use this? I know for sure that if I'm on the ground and I have the wind at my back, the winds aloft directly above me are to the right just a little bit further. I can make some assumptions. I can go ahead and start making these ad hoc assessments. I know where the winds aloft are where I am. I also know if the winds aloft at 6,000, 9,000 feet, wherever I'm flying at, and I want to get an idea maybe for where the winds are on the surface, or no surface observation, sometimes in untowered fields, nighttime, whatever. I know it's slightly to the left just a little bit. Just counterclockwise, 30, 45 degrees. All right.